In the heart of the Holy Roman Empire, a new era of cosmic understanding was about to dawn, setting the stage for a monumental shift in science. Johannes Kepler, born in 1571, was a man destined to rewrite the heavens. His early life was marked by illness and a deep, unwavering faith. A bout with smallpox at a young age left him with weakened eyesight and crippled hands, significant hurdles for a future astronomer. Despite these physical challenges, his intellectual prowess was undeniable, recognized by those around him. His academic journey led him to the prestigious University of Tübingen, where he initially enrolled to study theology. It was here he encountered the brilliant astronomer Michael Maestlin, who would become his mentor. Maestlin introduced Kepler to the heliocentric system of Nicolaus Copernicus, a controversial and revolutionary idea. Kepler was immediately captivated by the mathematical elegance and harmony of the Copernican model. He became a fervent, though private, advocate for the sun-centered universe, a dangerous position to hold. His first major work, the Mysterium Cosmographicum, was published in 1596. In this book, he proposed a model of the solar system based on the 5 platonic solids nested within each other. While the theory was incorrect, it showcased his genius for seeking mathematical laws in the cosmos. The publication brought him a degree of fame and notoriety within the scientific community. This work eventually caught the attention of the most famous astronomer of the age, Tycho Brahe. Tycho, a Danish nobleman, had built an astronomical observatory of unparalleled sophistication on the island of Heicheding. For decades, he had meticulously recorded the positions of stars and planets with astonishing accuracy. His data was a treasure trove, the most precise and comprehensive collection of astronomical observations ever assembled. In 1600, facing religious persecution in Graz, Kepler made the fateful decision to travel to Prague. He went to join Tycho Brahe, who had recently become the imperial mathematician to Emperor Rudolf II. The relationship between the two men was complex and often strained. Tycho was a flamboyant and secretive nobleman. Kepler was a pious and intense commoner. Tycho, protective of his data, was reluctant to share his life's work. He assigned Kepler the task of determining the orbit of Mars, a notoriously difficult problem. The orbit of Mars, with its apparent irregularities, had baffled astronomers for centuries. Tycho believed it would be a quick and simple task for his brilliant assistant, who was tragically mistaken. In a dramatic turn of events, Tycho Brahe died suddenly in 1601. After a struggle with Tycho's family, Kepler inherited the priceless collection of observational data. Now, with the treasure trove of celestial measurements at his command, his true war on Mars could begin. He spent years performing thousands of painstaking calculations by hand. He was armed with nothing more than pen, paper, and his formidable intellect. First, he tried to fit the orbit of Mars to a perfect circle, the shape favored since antiquity. He tried every variation imaginable, using epicycles and equants, the tools of the old astronomy. But a small, persistent discrepancy remained between his models and Tycho's data. The error was a mere 8 minutes of arc. Lesser minds might have dismissed it as an observational error. Kepler trusted Tycho's meticulous work implicitly. He famously declared that on these 8 minutes of arc, he would build a new astronomy. This refusal to compromise on empirical fact was a pivotal moment in the history of science. He abandoned the sacred circle, a shape that had dominated astronomical thought for 2 millennia. He began to experiment with other shapes, turning to the family of ovals. After immense struggle, a moment of sublime insight occurred. The orbit was not just any oval. It was a specific, mathematically precise shape. The orbit of Mars, and all planets, was an ellipse. This became Kepler's first law of planetary motion. The Sun was not at the center of the ellipse, but at one of its two foci. This simple statement completely overthrew the ancient ideal of perfect circular motion. But Kepler's work was not done. He had another mystery to solve. He noticed that planets did not travel at a constant speed. They sped up as they approached the Sun and slowed down as they moved away. He sought a mathematical law to describe this change in velocity. His genius revealed another profound secret of the cosmos. He discovered that a line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. This is Kepler's second law, the law of equal areas. It was a brilliant, non-intuitive discovery that connected a planet's position to its speed. Both of these revolutionary laws were published in his 1609 masterpiece, Astronomy Nova. The new astronomy provided the first physical explanation for the motions of the heavens, rather than purely mathematical ones. Kepler speculated that a force, a vis motrix, emanated from the Sun to move the planets. It was an embryonic, pre-Newtonian concept of gravity. The book was dense, difficult, and its conclusions were slow to be accepted. Even Galileo Galilei, a fellow Copernican, largely ignored Kepler's elliptical orbits. The world, it seemed, was not yet ready to abandon the perfection of the circle. Kepler's later years were filled with personal tragedy and the turmoil of the 30 Years' War. He was forced to move multiple times, constantly seeking a safe haven for his family and his work. In a particularly harrowing episode, he had to defend his own mother from accusations of witchcraft. Yet, through all this, his mind continued to search for the harmonies of the world. This quest culminated in his 1619 book, Harmonices Mundi. In this deeply mystical and mathematical work, he sought to connect astronomy, music, and geometry. Buried within its pages was the third, and final, game of his planetary laws. Kepler's third law relates a planet's orbital period to its average distance from the Sun. It states that the square of the period is proportional to the cube of the semi-major axis of the orbit. This harmonic law was the capstone of his celestial mechanics. It unified the entire solar system into a single, predictable, and harmonious whole. One could now calculate the period of a planet just by knowing its distance, or vice versa. Kepler's three laws provided the definitive mathematical proof for the Copernican system. They transformed astronomy from a descriptive science into a predictive, physical science. His work provided the crucial foundation upon which Isaac Newton would later build. Newton used Kepler's laws to derive his universal law of gravitation. Kepler had described how the planets moved. Newton explained why. Johannes Kepler died in 1630, a traveler to the end. He had unlocked the secrets of the heavens, but his work was not fully appreciated in his own lifetime. His epitaph, which he wrote himself, captured his life spirit. The laws that unlocked the heavens were the product of a unique mind. A mind that blended rigorous mathematics with mystical curiosity. A mind that respected data above all else. A mind that was brave enough to abandon 2,000 years of tradition. Johannes Kepler's legacy is written in the stars, in the silent, graceful dance of the planets. His work was a critical step in the journey of human understanding, from a mythical cosmos to a mathematical one. The heavens, once thought to be the realm of gods, were shown to be governed by knowable laws. This profound realization paved the way for the scientific enlightenment and the modern world. Every spacecraft we launch, Every planetary trajectory we calculate rests on the foundation he built. The war on Mars was won not with swords, but with mathematics. The prize was not territory, but a new and profound understanding of the universe. His dedication to precision transformed the very nature of scientific inquiry. He demonstrated that the universe was not only orderly, but also knowable through diligent effort. The shift from circles to ellipses was a paradigm shift of immense proportions. It taught us that the universe does not have to conform to our aesthetic prejudices. Truth, he showed, is found by listening to the evidence, not by imposing our beliefs upon it. His laws are a testament to a life spent in the relentless pursuit of cosmic harmony. The heavens Kepler unlocked were not just a physical space, but an intellectual one. He gave humanity the keys to the solar system, and we have been exploring it ever since. The story of Kepler is a powerful reminder that from great struggle can come great discovery. His life was a celestial orbit of its own, with moments of darkness and moments of brilliant illumination. He sought God in the geometric perfection of the universe. What he found were not Platonic solids, but three beautifully simple, empirical laws. And in them, he found a deeper, more profound harmony than he could have ever imagined. The meticulous data collected by Tycho Brahe, combined with Kepler's unparalleled mathematical genius, created a synergy that propelled scientific understanding forward by centuries. This collaboration, though sometimes contentious, ultimately yielded insights that neither man could have achieved alone. Kepler's ability to synthesize vast amounts of observational data into concise, universal laws remains a hallmark of scientific excellence. His laws are not just descriptions, they are predictions, allowing astronomers to accurately forecast the positions of planets far into the future. This predictive power is a defining characteristic of robust scientific theories. The shift from geocentric to heliocentric, solidified by Kepler's laws, was more than just a change in astronomical models. It was a profound philosophical shift, challenging anthropocentric views of the universe. His work paved the way for a mechanistic view of the cosmos, where natural laws, rather than divine intervention, governed celestial events. This mechanistic view was crucial for the development of the scientific revolution. Kepler's dedication to precision, even when faced with minute discrepancies, highlights the importance of empirical rigor in scientific discovery. He refused to force the data to fit his preconceived notions, a lesson that resonates through all scientific disciplines. The beauty of his laws lies in their simplicity and universality, applying to all planets in our solar system. By extension, his laws apply to the countless exoplanets we now discover orbiting distant stars. His work continues to be a source of inspiration for those who seek to understand the fundamental principles governing the universe. The story of Kepler and his elliptical orbits is a compelling narrative of human ingenuity, perseverance, and the relentless pursuit of knowledge. It reminds us that sometimes the most profound truths are hidden in plain sight, waiting for a mind courageous enough to see them. His contributions are not just historical footnotes. They are living principles that continue to inform and guide our exploration of the cosmos. The heavens, once a realm of mystery and divine intervention, became, through Kepler's eyes, a grand clockwork mechanism. This transformation in understanding was nothing short of revolutionary.